Welcome back to the Deep Dive, the show where we really try to cut through the noise and get you the knowledge that matters. Today we are diving deep, head first actually, into Python. It's that programming language that just seems to be everywhere, like the Swiss Army knife of the digital world. It powers huge web apps, drives data science, AI, you name it. So our mission today, give you that practical shortcut, help you get really well informed about Python's core strengths, maybe some of those pitfalls you don't always hear about, and just the whole amazing ecosystem around it. Think of this as your essential guide, giving you foundational knowledge, but also insights you can actually use.
It's true. Python really does stand out, doesn't it? It's got this unique mix. It's accessible enough if you're just starting, but it's also got the raw power for really complex, robust applications. And in this deep dive, we're definitely going beyond just, the what is Python definitions. We want to explore why it got so popular, dig into some of the more nuanced bits, and crucially, give you some insight into navigating its, let's say, unique challenges effectively. We've basically distilled down the key stuff from foundational text, community guides, practical experience, aiming for a really comprehensive picture.
Right. So settle in. We're really setting the stage here for a thorough look at how Python actually works. From its surprisingly interesting beginnings, right up to its role in today's cutting-edge tech. We'll cover, well, pretty much everything from the design choices behind its basic building blocks, all the way to strategies for keeping your apps running smoothly, efficiently, reliably, in the real world, in production. By the end, you should feel much better equipped to sidestep common headaches, write cleaner code, which is always good, and maybe even squeeze some extra performance out of your applications. Okay, so the story of Python itself is pretty remarkable. It feels like it's just everywhere now, right? Woven into almost every modern tech stack. But it wasn't like, bang, overnight success, was it? How did it climb to the top?
Oh, it's a fantastic story, actually. It really wasn't overnight. Python's journey started way back in the late 1980s. Guido van Rossum, he conceived it more as a hobby project, believe it or not, at CWI in the Netherlands. He was influenced quite a bit by a teaching language called ABC. ABC was known for being really simple, very straightforward. Yeah, and Guido's vision was basically to keep that beginner friendliness, that simplicity, but crucially add the kind of advanced features and extensibility that, professional developers would need for real-world stuff. And the name Python, it's kind of a fun anecdote. It was his nod to Monty Python's Flying Circus. He wanted a language that was powerful, sure, but also, enjoyable to use.
I was wondering about that.
Right. So the first public release, version 0.9.0, that came out in 1991, which, when you think about it, is actually quite early. It predates Java by 4 years, C++ by 6.
Wow, really?
Yeah. And his key decisions back then really set the stage. He prioritized simplicity and readability above almost everything else. He built in advanced features. He made sure it was good for everyday problems, not just academic ones. And critically, he made it free, open source, available online. Those choices, that combination, that was really the bedrock of its success, why it's still so popular today. It sort of democratized programming in a big way.
And that popularity now is, well, it's genuinely staggering, isn't it?
Yeah.
You look at something like the TIOBE index, which tracks language popularity. Python famously knocked Java and C++ off the top spot back in 2021, and TIOB's been tracking this since, 2001. That's not just a blip, that's a major shift in the landscape. What's really fascinating to me, though, is how it's broken out of just computer science departments. It's everywhere. Web development, obviously Instagram's built on Django, a Python framework.
That's right, yeah.
But then it's like the main language for data science, machine learning. And now you see it popping up in political science, finance, healthcare. It's truly one of the most widely used languages across such a huge range of fields. So if you're thinking about where to put your learning energy, understanding Python isn't just learning syntax. It's gaining this super versatile skill that's valuable now and seems, pretty future-proof given how broad its applications are. Yeah. So let's get down to brass tacks. For someone who's maybe dabbled in another language, written a hello world somewhere else, what are those really fundamental first line of code kind of design choices in Python that make it feel different? What jumps out immediately compared to, say, C++ or JavaScript?
That's a great way to put it, because Python's philosophy really hits you right away. It emphasizes readability and implicit structure in ways that feel quite distinct. Take indentation, for example. In a lot of languages, you use curly braces or keywords like begin to show code blocks. In Python, nope. Proper indentation isn't just good style, it is the syntax. It defines the structure. This forces a clean look, which is great for readability, but it can definitely trip you up at first if you're not used to white space being, well, significant.
Yeah, I remember that catching me out early on.
Exactly. Then there are variables. Python uses dynamic typing. This is a big one. You don't explicitly say, like, int count equals 0, like you might in C++. You just write count 0.
Ah.
Python figures out the type when the code runs. This makes development feel faster, more fluid, less boilerplate. But the flip side is you have to be a bit more careful because the type of data in a variable can change, and that can lead to runtime errors if you're not tracking it. So these aren't just minor tweaks. They really change how you think about structuring even simple programs. It pushes you towards more expressive, less cluttered code right from the start.
That dynamic typing and the significant white space. Definitely key differences. Okay, so we're writing our code, we have variables.
Yeah.
But what about the actual stuff our programs work with? The data itself, we need ways to categorize it. We all know basic data types, but what's Python's specific take? Where do the subtle distinctions really matter, especially for someone who might already know some programming?
Right, and this is where Python's approach, particularly around mutability, really comes into play and can be quite powerful, but also a source of bugs if you're not aware. You have your standard numerical types, int for whole numbers and float for numbers with decimal points. A neat thing about Python's integers, though, is they handle arbitrary precision. They can get incredibly large without overflowing, which isn't always the case in other languages.
It's useful.
It is. But the core distinction often boils down to whether a data type is mutable, meaning it can be changed in place after it's created, or immutable, meaning it can't. Let's run through the main ones with that in mind. Strings. Sequences of characters, your text data, enclosed in single or double quotes. Crucially, strings are immutable. Once made, you can't change a character within it. If you do something like misstring.upper, you're not changing the original, you're getting a new string back.
Okay, that makes sense. Immutable.
Integers, int, and floats.
Float.
Not numbers. As mentioned, int has arbitrary precision. Floats, like in most languages, can have tiny round-off errors because of how they're stored in binary. Also immutable. You can always check the type with the type function. Booleans, just true or false, used for logic, also immutable.
Right, the simple ones.
Lists. These are ordered collections in square brackets. And here's the key. Lists are mutable. You can add items, remove them, change existing items, all after the list is created. Super flexible, great for collections that need to change. They can hold different types too, like hello, 3.14, tuples. Tuple, similar to lists, ordered but defined with parentheses. The big difference. Tuples are immutable. Once you create a tuple, its contents are fixed. If you slice it, you get a new tuple. Good for data that shouldn't change, and they can be used as dictionary keys because they're immutable.
Oh, yeah. Okay, so lists change, tuples don't. That's the core difference.
Exactly. That's the takeaway. Dictionaries. These are collections of key value pairs inside curly braces, like Alice, age, 30. Keys must be unique and, importantly, immutable, so strings, numbers, tuples work as keys, but lists don't. Dictionaries themselves are mutable. You can add, remove, change key value pairs. They are super efficient for looking up values if you know the key. Sets. Also in curly braces, but they store only unique elements and they're unordered, like 1, 2, 3. Sets are great for membership testing, checking if something is in the set, removing duplicates, and doing mathematical set operations like union, intersection. Also mutable.
That mutable versus immutable distinction feels really central to Python's data model. It explains why some things work as dictionary keys and others don't, for example. Now, you mentioned strings and numbers. If you have, say, a price as a number and you want to put it in a sentence string, you can't just add them together, can you?
No, you can't. Not directly. And that leads us right into type conversion. Python is generally quite strict about types in operations. You can't just add a number to a string without telling Python explicitly what you want. So you use built-in functions like int, float, and stray to convert between types. If you have cost equals $10.50 and want the string $10.50, you'd need to write $ plus stray cost. You have to convert the float cost into a string first.
Got it. Explicit conversion.
Exactly. It makes the code clearer about what's happening and avoids ambiguity. So yeah, choosing the right data type, understanding if it's mutable or not, and knowing how to convert types when needed, these are fundamental for writing robust Python code. It really helps avoid subtle bugs down the line.
All right, so we've got our basic data ingredients, and we know how Python categorizes them, mutable or not. But programs aren't just about holding data. They need to do things with it, right? Interact, calculate, transform. How does Python let us manipulate this information effectively?
Absolutely, that's where the action happens. First off, arithmetic operations are pretty much what you'd expect. Plus, Python odd fun also gives you, for floor division, it divides and rounds down to the nearest whole number, giving you an integer result. And the percent modulo operator gives you the remainder of a division. Both and percent are super handy, especially for integer math. Then there's input and output. The print function is your main tool for displaying things. It's quite flexible. By default, if you give it multiple items, it puts a space between them. But you can change that separator using the sep argument, like print A, B, C, so it gives you ABC, and the end argument controls what's printed at the very end. Normally it's a new line, but you could change it to a space or nothing at all if you want subsequent prints on the same line.
Okay, cool.
For getting input from the user, you use input. It reads a line of text that the user types. One thing to watch out for, especially with online coding platforms, is you might need to provide all the input before running the script. If input is called, but there's no input left, you can get an EOFAIR end-of-file error. It's a common hiccup when starting out.
Right, I've seen that one.
Yeah, happens to everyone. Then we get into the really rich area of string manipulation and formatting. Python strings have a ton of built-in methods. You can easily change case with .lower and .upper. Slicing is incredibly powerful for pulling out substrings. The syntax is start.end. Remember, start is included, end is not. So times string 3.5 gets characters at index 3 and 4, maybe the minutes in. You can also use negative indices. Nec is a 1 is the last character. Nec is 2, the second to last, which is great for working from the end.
Negative indexing is super useful.
Totally. For searching, the in operator just checks if a substring exists, returning true or false, like A in banana. The count method tells you how many times it appears. Find gives you the starting index of the first occurrence, or mode of 1 if it's not found. Index is similar to find, but it raises a value error if the substring isn't there, which can be better if you expect it to be present.
Okay, find gives -1, index gives an error. Good distinction.
Exactly. Now, for putting strings together with variables, F strings, formatted string literals, are the modern preferred way. You just put an F before the opening quote, and then you can embed variables or even expressions right inside curly braces within the string, like F, hello, username, your score is score 10.
Super readable. Very convenient.
Yeah, F strings are great, much cleaner than the old ways. Agreed. But for more complex formatting, especially with numbers, you might still use the format method with format specifiers. These let you control things like the number of decimal places, number.2 for 2 places, padding with spaces or zeros, number.04d for a 4-digit integer with leading zeros, alignment for left aligned in a 10-character field. Lots of control there.
Right, for getting tables and reports looking just right.
Precisely. And finally, split and join string into a list of smaller strings based on a delimiter, a space by default. Join does the opposite. It takes a list of strings and joins them into one big string, using the string it's called on as the separator. So join.join hello world gives hello world. These are your core tools for working with text data slicing, dicing, formatting, and putting it back together.
Okay, so we have our data types. We know how to do basic operations, manipulate strings. But programs need to be smarter than just executing steps, A, B, C, right? They need to react, make decisions based on the situation. How do we give Python that kind of, well, intelligence?
That's exactly where control flow statements come in. They are the decision-making core of your program. The fundamental building block is the if statement. The structure is simple. If condition.body. If the condition part evaluates to true, then the indented block of code the body gets executed. If it's false, Python just skips that block.
Straightforward enough.
Yeah. Now, often you want an alternative path if the condition is not true. That's where else comes in, if condition. The key thing about if-else is that exactly one of those blocks will run. It's a fork in the road. You have to take one path.
Okay. Guarantees one or the other.
Right. But what if you have more than 2 possibilities? You might think of using multiple if statements. But if the conditions aren't mutually exclusive, you could accidentally run more than one block. That's why Python gives us elif, which is short for else if. You structure it like if condition 1, .elif condition 2, .elif condition 3. Python checks the conditions in order. The first one that's true gets its block executed, and then the entire structure is finished. None of the later elifs or the else are even checked. This ensures only one path is taken, even with multiple options.
So elif is crucial for making sure only one thing happens when you have several checks.
Precisely. It avoids unintended side effects. And of course, as we mentioned earlier, the indentation is critical here. Python uses indentation to know which lines of code belong to the if, elif, or else blocks. Consistent indentation isn't just style, it's syntax.
Makes sense. Now, those conditions, sometimes they're not just simple checks. Sometimes you need to combine things like, is the user logged in and do they have admin rights? Or is a value less than 0 or greater than 100? How do we handle that kind of compound logic?
That's where Python's logical operators are essential. You've got three main ones: and, or, and not, and. This requires both conditions on either side of it to be true for the whole expression to be true. If either one is false, the result is false. Or, this is more forgiving. It only needs at least one of the conditions to be true for the whole thing to be true. It's only false if both sides are false. Not. This one's simple. It just flips the truth value of whatever follows it. Not true becomes false, and not false becomes true.
Okay, and or not, just like logic class.
Pretty much. They let you build up complex decision criteria from simpler checks. Very powerful.
So with arithmetic operators, comparisons, and now these logical operators all potentially in the same line of code, there must be rules about which ones get evaluated first, right? Like PEMDAS in math.
Absolutely. Operator precedence is critical to avoid unexpected results. Python has a well-defined hierarchy. Generally, things happen in this order. 1, parentheses, override everything else. Use them liberally for clarity. 2, exponentiation, point 3. Unary plus minus, plus x 9x. 4, multiplication, floor division, unmodulo %. 5, addition, plus I, subtraction minus 6. Comparison operators, 7, not, 8, and 9, or. So, and is evaluated before or, and not is evaluated before both. Comparisons happen before the logical operators.
Okay, that order matters. What about operators at the same level, like multiplication and division?
Good question. That's where associativity comes in. Most operators in Python, including arithmetic and comparison operators, are left associative. That means they're evaluated from left to right. So 843 is treated as 843, which is 23 is 6.
Makes sense. Left to right, mostly.
The main exception is exponentiation would, which is right associative. So 234 is evaluated as 234, which is 281, a huge number, not 234, which would be 84. Again, using parentheses is often the best way to ensure your intention is clear, both to Python and to anyone reading your code.
Right. So we can make decisions. But computers are also fantastic at doing the same thing over and over again super fast. How do we tell Python, okay, do this thing 100 times, or keep doing this until some condition changes, without just copying and pasting code?
That's the job of loops, the core of automation and programming. Python gives us two main types. First, there's the while loop. The structure is while condition.body. It's pretty intuitive. Python checks the condition. If it's true, it executes the indented body of the loop. Then it goes back and checks the condition again. This repeats as long as the condition remains true.
Okay, keep going while it's true.
Exactly. The critical thing here is that something inside the loop's body usually needs to change eventually to make the condition become false. Otherwise,
You get stuck.
you get an infinite loop. Your program just keeps running that block forever or until you manually stop it. It's a classic beginner mistake. And sometimes even experienced programmers make it with complex conditions. You always need a way out.
Right, gotta make sure the condition can eventually become false. What's the other type of loop?
The other main one is the for loop. This is often considered more Pythonic for many tasks. Its structure is typically for loop variable in container.body. It's designed to iterate over the items in a sequence or collection like a list, a tuple, a string, or other iterable objects. For each item in the container, Python assigns that item to the loop variable and then executes the body. It handles moving to the next item automatically.
Ah, so you don't need to manage a counter variable yourself like you might in a while loop sometimes.
Often, no. If you're just processing each item in a list, the for loop is cleaner. If you do need to loop a specific number of times, you often use a for loop with the range. Range generates a sequence of numbers from 0 up to, but not including 5, so for I in line 5, is a common way to repeat something 5 times.
Okay, range is handy for that. Can you put loops inside loops?
Yep, absolutely. You can have nested loops. A loop inside another loop. This is common if you're working with, say, a grid or a list of lists where you need an outer loop to go through the rows and an inner loop to go through the items in each row. Loops are fundamental for automating repetitive tasks.
So loops keep going until they're done or the while condition is false. But what if you're halfway through a loop and you realize, okay, I found what I need, or this particular item is bad, just skip it and go to the next one. Can you jump out early or skip an iteration?
Yes. Python gives you specific commands for that kind of fine-grained control: break and continue. The break statement immediately exits the entire current loop, the innermost one if they're nested. Execution jumps straight to the first line of code after the loop finishes. It's perfect for when you've found your target in a search or an error condition means you can't continue.
Okay, break, get you out completely.
Right. Then there's continue. This statement skips the rest of the current iteration's code block and immediately jumps back to the top of the loop to start the next iteration. For a while loop, it rechecks the condition. For a for loop, it gets the next item. It's useful when you want to process most items but skip certain ones based on some criteria without stopping the whole loop.
So continue skips the current round but stays in the loop.
Exactly. And Python has one more slightly unusual feature with loops, an optional else block. You can write for, hell else, or while else. This else block executes only if the loop completes normally, meaning it finished all its iterations, for, or the condition became false, for while, without ever hitting a break statement.
Huh. When would you use that?
A common use case is searching. You loop through a list looking for something. If you find it, you break. The else block associated with the loop could contain code that runs only if the loop finished without finding the item, i.e. no break occurred. It's a neat way to handle the not found case. So yeah, break, continue, and the loop else give you really precise control.
Okay, this is great. We're building up complexity. But as programs get bigger than just a few loops and conditions, maybe hundreds or thousands of lines, just having one long script becomes, well, a nightmare to manage, right? Well, how do we organize things better, make code reusable so we're not just copying and pasting the same logic all over the place?
You've hit on a fundamental principle of software design, modularity. And in Python, the primary tools for this are functions and modules. Let's start with functions. A function is basically a named block of code that performs a specific task. You define it using the def keyword, like def greetuser, name.print, f, hello, name. The benefits are huge. Organization breaks down complex problems into smaller logical chunks. Reusability, write the logic once, call the function multiple times from different places, no more copy-paste. Readability gives a descriptive name to a piece of logic, making the main part of your code easier to follow. Maintainability. If you need to change the logic, you only change it in one place, the function definition.
Right, that makes perfect sense. Define it once, use it many times.
Exactly. And good functions often include docstrings. These are triple quoted strings placed right after the def line. They explain what the function does, what arguments it expects, and what it returns. They're super important for documentation and can be accessed using help function name.
Ah, so that's what those triple quotes are for.
Yeah.
Uses them.
Yep. Now, when you call a function, like Greedos or Alice, the program's control jumps into the function, executes its code, and then usually returns back to where it was called from. Functions can optionally return a value back to the caller using the return statement. If there's no explicit return, the function implicitly returns a special value called none.
Okay, and you mentioned arguments, like Alice in your example. What's the deal with passing data into functions?
Right, so the names in the function definition, like name in def greetuser name, are called parameters. The actual values you pass when you call the function, like Alice, are called arguments. How Python handles this passing is sometimes called pass-by-object reference, which can be a bit subtle. When you pass an argument, the function's parameter gets a reference to the exact same object in memory. Now here's when mutability matters again. If you pass a mutable object, like a list, and the function modifies that object, like appending an item, that change will be visible outside the function because both the original variable and the parameter point to the same list object.
Ah, so changing a list inside a function can change the original list.
It can, yes. But if you pass an immutable object, like a number or a string, the function can't change the original object itself. If the function reassigns the parameter variable, gname inside the function, it just makes the parameter point to a new object locally. The original variable outside the function remains unchanged. Understanding this difference is crucial.
Definitely sounds like something to watch out for.
It is. Python also supports keyword arguments, where you explicitly name the parameter when calling, like calculataria length 10 with 5. This improves readability, especially for functions with many parameters, and means the order doesn't matter. You can mix these with regular positional arguments where order does matter. Functions can also have default parameter values defined, like def powerbase exponent 2. This makes the exponent argument optional. If you don't provide it, it defaults to 2. One quick warning. Avoid using mutable objects like lists or dictionaries as default values. They get created only once when the function is defined, not each time it's called, which can lead to very confusing shared state bugs.
Okay, mutable defaults are bad. Got it.
Good rule of thumb. Finally, there's variable scope. Variables defined inside a function are local to that function. They only exist while the function is running and can't be accessed from outside. Variables defined outside any function are global. They can be accessed from anywhere, including inside functions. If you need to modify a global variable from within a function, you have to explicitly tell Python using the global keyword, like global counter. However, relying heavily on global variables is often discouraged as it can make code harder to understand and debug. And be careful, if a local variable has the same name as a global one, the local name takes precedence inside the function, which can sometimes hide the global variable unexpectedly. Functions are like your custom toolkit. Scope rules define where those tools work.
Okay, functions help organize code within a single file. But what about really big projects, or when we want to use code written by someone else, maybe from the community? We can't just put everything in one giant .py file, can we?
No, absolutely not. That's where modules come in. A module is simply a Python file, a .py file, containing Python definitions and statements, functions, classes, variables. They allow you to break your project into multiple files, organizing related code together. To use the code from another module, another file, you use the import statement. Import math brings in the entire math module, and you access its contents using dot notation, like math.sqrt16.
Okay, import pulls in the whole file.
Right. Or if you only need specific things, you can use from module import name1, name2, like from math import squirt py. Then you can use squirt directly without the math.prefix. A word of caution here. If you import names directly like this from multiple modules and they happen to use the same name, you can get name collisions, where one import overwrites the other.
Ah, okay. So import module is safer sometimes.
It avoids name collisions, yes. Another option is aliasing when you import. Import very long module name as VLMM. Then you can use VLMN.function, which is shorter. Or from math, import squirt as square root. Now, a really crucial concept with modules is the if name equal main.block. Here's the thing. When you import a module, Python actually executes all the top-level code in that module file, any code that isn't inside a function or class definition.
It runs the code just by importing it.
Yes, which might not be what you want if the module file also contains, say, example usage or test code. The if name equals main.idiom solves this. Code inside this block will only run when the file is executed directly as the main script. It will not run when the file is imported as a module into another script. Python automatically sets the special variable name to the string main for the script that's run directly. For imported modules, name is set to the module's file name.
Okay, that's super important. Put script running code inside if name equals main.
Exactly. It's the standard way to make a Python file usable, both as a runnable script and as an importable module. You might also see other dunder double underscore variables like the module's docstring, or file the path to the module file. And where do these modules come from? Well, there's the Python standard library, a huge collection of modules included with Python itself for common tasks like working with dates, files, networking, etc. Then there's the Python package index, PyPI, which is a massive online repository of third-party packages developed by the community. You use a tool called pip, usually comes with Python, to install these packages like pip install requests. This whole system functions, modules, the standard library, PyPI, pip is what makes Python so powerful. It allows developers to easily share and build upon each other's work, enabling the creation of incredibly complex applications relatively quickly.
All right, so we're writing our code, structuring it with functions and modules. Things are looking good. But let's be honest, errors happen all the time. It's not if, it's when. So when Python inevitably throws up its hands and complains, how do we even start to figure out what went wrong?
You're absolutely right. Errors are just part of the process. And honestly, getting good at debugging, finding, and fixing errors is probably one of the most critical skills a developer learns. It's not just about fixing the immediate problem. Understanding why it happened helps you avoid similar mistakes later. When Python encounters an error it can't handle at runtime, it doesn't just crash silently, it generates what's called a traceback. This traceback message can look intimidating at first, but it's actually your best friend.
Yeah, that wall of text can be scary.
It can. But don't fear the traceback. It's Python literally tracing back the sequence of calls that led to the error, trying to give you as much context as possible, it tells you. The file name where the error occurred, the specific line number within that file. Often the line of code itself, sometimes with a little caret pointing to the exact spot Python thinks the problem is, and most importantly, the type of error like syntax error, name error, value error, and a specific error message, which often gives clues or even suggestions. Like if you forget parentheses and print hello, it might say syntax error. Missing parentheses and call to print. Did you mean print hello?
Oh, that's actually helpful.
That really is. Or if you miss a colon in a dictionary, like employees PAM30, you'll get syntax error dot invalid syntax. Or forgetting a closing parenthesis might give syntax error unexpected EOF while parsing. EOF means end of file. So think of the traceback not as a failure message, but as a detailed diagnostic report pointing you right to the scene of the crime.
Okay, a diagnostic report. I like that framing. So what are the common ailments this report might diagnose? If we can recognize the types of errors, that must speed things up, right? Like knowing the difference between a cold and the flu.
Exactly. Recognizing the patterns is key. You'll see certain types of errors crop up again and again. Here are some of the most common categories. Syntax error. These are like grammatical mistakes. Python literally can't understand the code as written. Things like unclosed quotes, incorrect indentation, using assignment when you meant comparison, misspelling keywords, while instead of while, missing colons, brackets, parentheses. The parser just stops.
The basic typos and structure mistakes.
Yep. Then you have errors related to accessing things. Name error. Trying to use a variable or function name that hasn't been defined yet or isn't available in the current scope. Often just a typo. Key error. Trying to get a value from a dictionary using a key that doesn't exist, like mydict non-existent key. Index error. Trying to access an item in a list, tuple, or string using an index number that's out of bounds, for example, asking for the 10th item in a 5-item list. Attribute error. Trying to access a method or attribute on an object that doesn't have it, like calling .append on a tuple, since tuples are immutable and don't have append. Module not found error. Happens when you try to import a module that Python can't find. Maybe it's not installed or there's a typo in the name.
Okay, so these are all about trying to reach something that isn't there or isn't accessible?
Precisely. Then there are errors about data suitability. Type error. Trying to perform an operation on a type of data that doesn't support it, like trying to divide a string by a number, hello 3, or trying to loop over an integer, you can only loop over sequences, or passing the wrong type of argument to a function, like giving len an integer instead of a list or string. Value error. The data type is correct, but the specific value is inappropriate for the operation. Like int ABC, ABC series is a string, which int accepts, but its value can't be converted to an integer. Or math.sqrt-1 scored expects a number, but can't handle a negative value in standard math.
Yeah, the type is right, but the value is wrong. Subtle difference.
It is, and a few others. Unbound local error. Using a local variable within a function before you've actually assigned a value to it in that function's scope. Zero division error. Pretty self-explanatory, attempting to divide by 0. File not founder. Trying to open a file that doesn't exist at the specified path. Memory error. Your program trying to allocate more memory than the system has available. Permission error. Your program doesn't have the operating system rights to read or write a file or access a resource. You don't need to memorize this whole list, but recognizing these common categories helps you diagnose problems much faster by pointing you in the right direction based on the error type reported in the traceback.
Okay, so errors happen. We can read the traceback, we recognize the common types. But ideally, our programs shouldn't just crash and burn when something unexpected happens, especially if it's something like bad user input. Can we make our code more resilient? Can it handle errors gracefully?
Absolutely, and that's a critical part of writing robust software. Python provides a mechanism called exception handling using try and except blocks. The idea is simple. You put the code that might cause an error, an exception, inside a try block. If an error does occur within that block, Python immediately stops executing the rest of the try block and jumps to the corresponding except block.
So it catches the error.
Exactly, catch the exception. You can specify which type of exception you want to catch, like except value error. If a value error happens in the try block, the code inside the except value error block runs. You can have multiple except blocks to handle different types of errors. Or a general except that catches any exception, though it's usually better to be specific. For example, if you're converting user input to a number, python.age, enter age, hashtag, maybe do something with age.
Invalid input. Please enter a number. None. Hashtag yes, or set a default, or ask again.
Now, if the user types hello instead of crashing with a value error, the program prints a helpful message and can continue running, perhaps using none for age or prompting again. This makes your code much more user-friendly and stable. It's how professional applications handle unexpected situations without falling over.
That's incredibly useful, building
Yeah.
in that resilience. But what if our code detects a problem? Like a function gets an invalid input that isn't necessarily a built-in error type, but it's logically wrong for our application. Can we signal an error ourselves?
Yes, definitely. And that's done using the raise statement. Raise allows you to manually trigger an exception. You typically raise one of the built-in exception types, like value error, type error, etc., or you can even define your own custom exception classes. When your code detects a situation that it considers an error, maybe invalid data, an impossible state, you can raise an appropriate exception, often with a descriptive message. For instance, in a pizza class, if someone tries to create a pizza with an invalid size, Python. Valid sizes, small, medium, large. Define itself size. If size, not invalid sizes. Raise value error. F, invalid pizza size. Must be one of valid size. Raise value error. F, invalid pizza size, dot size. Now, if someone tries pizza extra large, it won't silently create a bad object. It will immediately raise a value error, stopping execution at that point and signaling clearly that something is wrong. This is crucial for enforcing rules and ensuring the integrity of your program's state.
Okay, so we can catch errors with try except and signal them with raise. But beyond just fixing things when they break during development, how do we get visibility into what our program is doing, especially once it's running live, in production? Fixing bugs is one thing, but proactively understanding behavior and finding issues seems critical.
You're absolutely right. Moving beyond reactive bug fixing requires proactive strategies, and two pillars here are logging and debugging tools. For any application running in production, a solid logging strategy is non-negotiable. Instead of just using print statements, which often get lost or aren't structured, you should use Python's built-in logging module. It's been part of the standard library forever, since Python 2.3. It allows you to record events, messages, and errors in a structured way. You can configure different logging levels to control the verbosity. Debug, very detailed info, mostly for diagnosing problems. NFO, confirmation that things are working as expected. Warning, something unexpected happened or a potential problem, but the app is still working. Default level, error. A more serious problem, couldn't perform some function. Critical, a very serious error. The program itself might be unable to continue.
So you can filter messages based on severity.
Exactly. You can easily configure logging to, say, only record INFO level and above to a file, while perhaps showing debug messages on the console during development. A typical setup might look like logging.basicconfig level logging.info, file name app.log, format %s times %level names messages. This sends messages to app.log, includes timestamps and levels, making it much easier to trace what happened when. In production, these logs are often shipped to a central logging system like the ELK stack, Splunk, or services like BetterStack, where they can be searched, monitored, and used to trigger alerts if error rates spike. Logging gives you that crucial historical record.
Okay, logging for the long view. What about digging into problems right now during development?
For that interactive deep dive, you use a debugger. Python's built-in debugger is called PDB. It's a command line tool, but incredibly powerful. You can insert the line import PDB, pdb.settrace anywhere in your code. When Python hits that line, execution pauses, and you're dropped into the PDB interactive prompt right there in your terminal.
Like freezing time inside your code.
Pretty much. From the PDB prompt, you can step through your code line by line, S for step into functions, N for next line, inspect the value of any variable, P variable name, see where you are in the code, L for list, continue execution until the next breakpoint or the end, C for continue, even execute arbitrary Python code in the current context. It lets you really dissect the program's state at a specific point and understand why it's behaving unexpectedly. For example, if you used XOR instead of power, PDB would let you inspect the variables right before and after that line and immediately see the wrong result. It's invaluable for tracking down tricky logic errors that a simple traceback might not fully reveal. Logging gives you the history. PDB gives you the real-time inspection. Both are essential for robust code.
Okay, we've laid a really solid groundwork. The basics, the logic, handling errors. Now let's shift gears a bit towards building more complex, more organized systems. We often hear about object-oriented programming, OOP. It sounds like a big deal. What's the core idea behind OOP in Python, and why is it considered such a powerful way to structure code, especially for larger projects?
OOP is definitely a major paradigm, a different way of thinking about structuring programs. Instead of just having procedures acting on data, OOP encourages you to bundle data, attributes or fields, and the behavior methods or functions that operates on that data together into logical units called objects. Imagine modeling a car. An object-oriented approach would create a car object that holds its own data, like color, speed, fuel level, and also contains the methods to act on that data, like accelerate, brake, refuel, the main advantages. Clear structure. It maps well to real-world concepts, making complex systems easier to understand. Maintainability and modification. Changes related to one type of object are often localized within its definition, reducing ripple effects. Reusability. Concepts like inheritance allow you to reuse code effectively.
Okay, bundling data and behavior. What are the main principles? I hear terms like encapsulation, inheritance.
Right. OOP is often explained through its four main pillars. 1. Encapsulation. This is about hiding the internal details of how an object works and exposing only a necessary simplified interface. It protects the object's internal state from accidental modification. In Python, we don't have strict private keywords like Java or C++bo, but we use a convention. A single leading underscore, e.g. internal data, signals this is intended for internal use, please don't mess with it directly from outside the class. It's a gentleman's agreement relying on convention.
So underscore means hands-off, probably.
Pretty much. It promotes cleaner interfaces. 2. Abstraction. Closely related to encapsulation, abstraction focuses on hiding complexity and showing only essential features. Think of your car's dashboard. It abstracts away the complex engine mechanics and just shows you speed, fuel level, etc. 3. Inheritance. This allows a new class, a subclass or child class, to inherit attributes and methods from an existing class, a superclass or parent class. This is fantastic for code reuse. You could have a general animal class and then dog and cat subclasses that inherit common animal behaviors but add their own specific ones. Often, the subclass constructor will call the parent's constructor using super.in to make sure the inherited parts are set up correctly.
Like building on existing blueprints.
Exactly. 4. Polymorphism. This literally means many shapes. It allows objects of different classes to respond to the same method call in their own specific ways. If both dog and cat classes have a speak method, calling speak on a dog object might print woof, while calling it on a cat object prints meow. The same interface speak leads to different behaviors depending on the object's type. This also includes operator overloading, where you can define special methods like add for plus, double len for len, strat for score to make standard Python operators and functions work naturally with your custom objects.
Making your own objects behave like built-in ones. Cool.
Yeah. So the core building blocks are classes. The blueprints, defined with class name, and instances, the actual objects created from the blueprint, like my car, produce des. The special init method inside a class is the constructor. It's called automatically when you create an instance and is used to initialize the object's attributes, its data. OOP provides this powerful framework for modeling complex systems in a more organized, flexible, and maintainable way.
Now, Python gets tons of praise for being readable, easy to learn, which is great. But sometimes you hear the criticism that it's slow, especially compared to languages like C++ or Go. Is that fair? And if performance really matters for a specific application, what can we actually do to make Python faster?
That's a really common topic, and the answer is nuanced. Is CPython, the standard implementation, inherently slower than compiled languages like C++ or Go in raw computation benchmarks? Yes, often significantly you might see differences of 30, 40x or more in CPU-bound tasks. There are reasons for this. It's interpreted. Code is translated on the fly, not pre-compiled to machine code. It's dynamically typed, checking types at runtime, adds overhead. And maybe the most discussed factor, the global interpreter lock, GIL.
Ah, yes, the GIL. Heard of it.
Right. The GIL is basically a mechanism in CPython that means only one thread can hold control of the Python interpreter at any given time, even on multi-core processors. This simplifies CPython's memory management, but effectively prevents standard Python threads from achieving true parallelism for CPU-bound code. They're great for I/O-bound tasks, waiting for network or disk, but not for crunching numbers across multiple cores simultaneously.
So multiple threads don't always mean multiple times faster for calculations.
Exactly, not with standard threading for CPU work. However, and this is a big however, for a vast majority of real-world applications, Python speed is perfectly adequate. And when it's not, performance optimization in Python is very achievable. It's often about writing smarter code, not necessarily switching languages, profiling first. Don't guess where the bottleneck is. Use tools like cprofile or timemate to measure where your code spends its time. Optimize the hotspots, algorithm and data structures. This is often the biggest win. Using a more efficient algorithm, switching from ON2 to ON-log-n, can yield orders of magnitude improvement, far more than micro-optimizations. Use built-ins and optimize libraries. Python's built-in functions and standard library modules are often written in C. Libraries like NumPy, Pandas, scikit-learn are highly optimized C or Fortran code under the hood. Use them whenever possible for numerical tasks.
Leverage the C code hidden inside Python libraries.
Precisely. Caching. If you have expensive function calls that get called repeatedly with the same arguments, cache the results. Python's functools.go decorator makes this incredibly easy. Memory optimization. For classes where you create many instances, using slots can significantly reduce memory usage by predefining attributes, which can indirectly improve speed by reducing garbage collection pressure. Avoid unnecessary work. Simple things like moving calculations out of loops if they don't need to be repeated. Regarding numbers, watch out for potential floating point inaccuracies. 0.1 plus 0.2 isn't exactly 0.3 due to binary representation. For integer division where you need the whole number result, use floor division my and use the modulo operator % for the remainder. For measuring small snippets, the time module is your friend. It runs code multiple times and gives you reliable timings. Great for comparing two different ways of doing something. And there are powerful tools to help. Static analysis tools like DeepSource can analyze your code without running it and automatically suggest performance improvements or find inefficient patterns. Codicy also offers automated reviews. For critical CPU-bound sections where pure Python is just too slow, Python is amazing. It lets you write code that looks almost like Python but compiles down to C code, often giving massive speedups for those specific parts without needing a full rewrite.
Wow, okay, so the slowness is real in some contexts, but often manageable or solvable with the right techniques and tools. It's not necessarily a deal breaker.
Exactly. For most use cases, Python's developer productivity and rich ecosystem far outweigh the raw speed difference. And when speed is critical, you have options.
So with that performance picture clarified, where does Python really make its mark today? What are the big areas where people are building amazing things with it?
Oh, it shines in so many places. Two huge ones are web development and data science. In web development, Python is a major player for building the back-end logic of websites and APIs. There's a whole ecosystem of frameworks. Django, this is the big batteries included framework. It provides tons of built-in features for things like database access, ORM, admin interfaces, authentication. It's great for building complex, data-driven web applications quickly. Think Instagram, Pinterest.
The all-in-one solution.
Pretty much. Then you have Flask. It's a micro-framework, much more lightweight and flexible. It gives you the basics and lets you choose the other components you want to add. Great for smaller apps, APIs, or when you want more control. Fast API. This one has gained massive popularity recently. It's built for speed, leveraging modern Python async features, and is fantastic for building APIs. It has automatic interactive documentation and data validation built in, which developers love, often used for ML model serving too.
Heard a lot about Fast API.
Yeah, it's very hot. There's also Sanic, another async framework known for speed, and others like Likestar. On the simpler side, Anvil lets you build web apps entirely in Python, including the UI, which is interesting. Often, the Python backend is paired with a JavaScript frontend, using frameworks like React or Vue or mobile apps. And a key library pretty much everyone uses is requests for making HTTP calls to other services or APIs. You'll install that with pip.
Okay, web dev is huge. What about the other big one, data science?
Data science. This is arguably where Python dominates. It's become the de facto standard language for data analysis, machine learning, AI, the whole workflow, data acquisition and cleaning. Getting data from various sources, handling missing values, fixing inconsistencies, exploration and analysis, EDA, digging into the data, calculating statistics, finding patterns, modeling, building predictive models using machine learning algorithms, visualization, creating charts and graphs to understand and communicate results. Python has killer libraries for every step. NumPy, the absolute foundation for numerical computing, provides efficient array objects, owned array, and mathematical functions. Pandas, built on NumPy, provides data frame objects, think superpowered spreadsheets and code, essential for data manipulation, cleaning, analysis. Functions like .head, .describe, .groupb, .filna are used constantly.
Pandas is everywhere in data science code.
Absolutely essential, Matplotlib and Seaborn, for creating all sorts of static, interactive, and animated visualizations. Bar charts, line plots, scatter plots, heat maps, crucial for understanding data. Scikit-learn, the go-to library for traditional machine learning algorithms, classification, regression, clustering, etc. TensorFlow and PyTorch, the heavyweights for deep learning. And tools like Jupyter Notebooks and cloud versions like Google Colab provide an interactive environment perfect for data exploration, combining paired visualizations and text.
It really is an incredible ecosystem. And quickly, what about the tools developers use to actually write this code?
Good point. For serious development, most people use an integrated development environment, IDE, or a sophisticated text editor. IDEs like PyCharm are very popular. They offer intelligent code completion, debugging tools, testing integration, version control support, all in one place. VSCode, with Python extensions, is also extremely popular and flexible. For simpler tasks or scripting, powerful text editors like Sublime Text, Atom, or even Notepad++ on Windows, with Python syntax highlighting, are often enough. The choice often comes down to personal preference and project complexity.
Makes sense. The tooling around Python seems just as rich as the language itself. So we've covered the function, the performance, the applications. But what about the form? How the code actually looks on the page? Does that really matter? Why is there so much emphasis on code style and readability in the Python world?
Oh, it matters hugely. It might seem secondary, but think about it. Code is read far more often than it's written, especially in team environments or when you come back to your own code 6 months later. Readability is paramount for maintainability, collaboration, and reducing bugs. Unclear code is hard to understand, hard to modify correctly, and easy to break. The Python community places a very high value on this, and the main guide is PEP8. That's Python Enhancement Proposal number 8, the official style guide for Python code. It covers things like indentation. Use 4 spaces per indentation level. This is strongly preferred over tabs. Line length. Keep lines under 80 or sometimes 100 characters. Blank lines. Use them judiciously to separate logical sections or functions. Imports. How to order and format import statements. White space. Consistent use around operators and commas. Naming conventions. This is a big one for readability.
Right, you mentioned naming earlier. What are the standard conventions from PP8?
Generally, lowercase or lowercase with underscores, snake case. 4. Module names, function names, method names, variable names. Capitalized words, camel case or Pascal case 4. Class names and exception names. All caps with underscores for constants. Variables whose values shouldn't change. Following these conventions makes code instantly more familiar and easier to scan for anyone used to reading Python.
Consistency is key.
Absolutely. PTIP also touches on comments and docstrings. Comments, hashtag should explain the why, not just the what. Docstrings, triple quotes, are for documenting what modules, classes, functions, or methods do, their arguments, return values, etc., essential for anyone using your code, including future you. And back to that private variable convention, the single leading underscore variable name. It doesn't prevent access, but it clearly signals this is an internal implementation detail. Respecting that convention helps keep code bases cleaner and less brittle when internal details change. Adhering to Petit isn't just about making code look pretty, it's a sign of professionalism and makes the entire ecosystem easier to work with. Hashtag tag outro.
Wow. Okay, that was genuinely a deep dive. We've really journeyed through the Python landscape today. From its surprisingly humble beginnings and unique design choices, through the core syntax, tackling errors, boosting performance, right up to seeing it in action in web dev, data science, and the importance of writing clean code.
It really covers a lot of ground, doesn't it? But hopefully what comes through is how Python's core philosophy that focus on readability, the power of its libraries, the way it handles errors, all contributes to why it's so enduring and versatile. It's a language that genuinely empowers people to build interesting things across so many different fields.
So for you listening, what's the takeaway? You should now have a much stronger grasp of not just Python's capabilities, but also its underlying principles and how to navigate some of its specific quirks and challenges. Whether you're starting out or looking to level up, these insights should really help you build more effective, robust applications.
Exactly. And remember, learning Python, like any language, is an ongoing process. The concepts we talked about today, understanding tracebacks, leveraging modules, writing clean code, knowing when and how to optimize, these are the fundamentals you'll keep coming back to. Python's strength isn't just the syntax, it's the whole ecosystem, the community conventions, the helpful error messages. It all works together.
Definitely. So as we wrap up, here's maybe a final thought to chew on. We've seen how adaptable Python is, and we know fields like AI and data science are exploding, largely powered by Python. Thinking about its core principles, readability, modularity, that strong community, how might these very characteristics shape the future of programming itself? What kinds of completely new problems, or maybe things we can't even properly imagine today, will Python be tackling in the next 5 or 10 years? Something to think about.